So we've already taken a look at the basics of force, its units, even a little bit of gravity and how it plays an acceleration and a force, and the difference between mass and weight. It's time to look at where we get all of our basic understanding when it was first systematically done by Newton in his 3 laws of motion. Yes, motion, because force and motion are related. Newton's first law, it states an object at rest stays at rest, an object in motion stays in motion with the same speed in the same direction, so same velocity, unless acted upon by an unbalanced force. It's also known as the law of inertia, because we said earlier, inertia is just a term for things not wanting to change their motion. Newton's first law says it's going to take an unbalanced force to make things move differently than they're already moving. So if it's sitting still, you have to apply a force to get it to move. If it's moving, a force has to be applied to stop it. So this can be seen in some neat little experiments. If you have like a little tray on wheels that's rolling down a ramp and you put a blockade in front of it, like down here, if you have loose things on top, you're applying a force to the cart, but it isn't applied to the things there, so they fly forward because of their inertia. And one you can do at home, fill up a glass and put a playing card over top of it and set a quarter on top of that. If you flick the card just to the side, you're only exerting force on the card, making it move, but that coin doesn't want to move because of its inertia, and so it'll end up dropping down into the glass. It's fun. Give it a shot. Newton's second law. In the way he stated it, it's the acceleration of an object is directly proportionate to the magnitude and direction of the applied force, but is inversely proportional to the mass of the object. But as I've seen over the years, when I give people the exact meaning or exact phrasing of Newton's second law, they go, what are you talking about? That doesn't make no sense. So let's break it down a little bit. Really, all that second law is stating is that there is a mathematical relationship between force, mass, and acceleration. So when it starts to talk about the acceleration is directly proportional to the force, but inversely proportional to the mass, it's talking about F equals ma, it's just writing it different. It's writing it solved for A. Remember our triangle, and you can solve this for any of the 3 variables. So if I cover the A, I have force divided by mass. Well, acceleration is going to be equal to force. Force is on top, so it's in the same level as acceleration, divided by mass. Meaning, the mass, the bigger it gets, the less acceleration. The bigger the force gets, though, the bigger the acceleration. Here's a different visual to try to get you to understand that. So if force goes up, you can either increase the mass or you can increase the acceleration because those are multiplied towards each other. But if you're going to keep like force the same, then you would have to decrease either acceleration or mass and increase the other one inversely. Thus that term inversely. Now, basically, you just need to know this formula and how to manipulate it in the triangle that we showed you a minute ago. Okay? You got to solve for mass or solve it for acceleration or solve it for force. If we're going to do that, I'm going to show you all 3 forms. This is solve for force. We saw a minute ago, acceleration is equal to force divided by mass. And we could say that mass is going to be equal to, and that would be force divided by acceleration. So remember, if you're not good at using the triangle, be good at algebra or write those in your notes. Newton's third law, and one of the most fun. For every action, there is an equal and opposite reaction. So we tend to use that a lot to talk about all kinds of stuff, even arguments. They say, well, if I start arguing, someone's going to argue back. But it really is talking about force. And so one of the greatest ways I know to do this, and I really like this, if you have a balloon at home, go ahead and do this. Blow up a balloon, and now you've applied force in there, and you're going to have an elastic force wanting to squeeze that air out. Well, if you let go of it, that air does in fact squeeze out, and it creates a force on the rest of the air in the room. Well, that other air creates an equal force on the balloon, and that's why it goes all around the room. It's equal and opposite forces reacting with one another. It's a great thing. This also is the force that keeps you from falling through your chair when you sit on it. If you sit down in a chair, you apply a force onto the chair. Well, if the chair didn't apply a force back, you would end up falling through onto your butt. Newton's third law is often shown in free body diagrams. So in physics, we love our pictures because they allow us to see what's going on in things. I enjoy this tiny little baby trying to lift this massive amount of weight. Now, if we think about just the barbell, we can draw the forces that are acting right there. Because it has a weight, that's going to be acting downward, right? And that we're just going to say the force of gravity. Remember, big F, subscript G, okay? But it's not going through the floor. So it's not falling down, meaning the floor has to be exerting a force upward that is equal to the force of that gravity, okay? So it would be equal to the force of gravity going upward. And this free body diagram shows that those forces are going back and forth. Now, we can add further because I'm assuming this cute little baby is actually trying to lift this bar. That means the baby is exerting a force up. I'm going to call this the force of the baby. Okay? But it's not moving, so I know that the bar has to be exerting an equal force in the opposite direction to the baby. So I'm going to call that the force of the bar. That has to cancel it out. Otherwise, that baby would be able to lift this huge thing if there was no force being applied back. Now, I know it's odd to think of inanimate objects applying a force, but that's really what's happening with Newton's third law. Anytime you have an action, like a force applied on something, there has to be an equal force applied back. Unless there's movement, then we call it an unbalanced force. And there's still an equal and opposite reaction, it's just this force can't reach the amount of force that the baby can put on it. So the baby would have to apply more force to the bar than the bar can apply to the baby in order to get it to move up. And this, drawing things out with arrows and little designators like this, is called a free body diagram. Kind of. We don't normally do it on a picture like this. We normally do it on a dot. So in physics, normally I would want to do my free body diagram saying I'm talking about an object. So I'm going to talk about the bar, all right? So that's my object. And I call this a dot because we're looking at the center of mass and where all the forces apply. Now we said before that the baby is applying a force up. We called that the force of baby. And we said that had to be equal to the force of the bar because it's being applied down. Now, we also said on that weight, that big dumbbell, that there had to be a force of gravity being applied downward, right? But it wasn't falling through the floor, so we also know that it had to have an equal amount of force from the floor, right? And we can write out some equivalencies in this. Because of Newton's third law, we call what we have now is Newton's third law pairs. And so all that means is that F of baby, let's redo that, is equal to the force of bar. And then we also have that the force of gravity, let's write that a little better too, is equal to the force of floor. And these are called Newton's pairs, Newton's third law pairs, because they're equal and opposite forces. For every action, there's an equal and opposite reaction. Okay? Now, technically, to make these true, I would have to say that these are magnitudes. So I'm not looking at direction, because force, guess what? It's a vector, not a scalar, so it has a direction. So Newton pairs, and if you've never seen this symbol before, these lines just mean you're not worried about negative or positive, just the magnitude. The magnitude of this is equal to the magnitude of that. Magnitude of this is equal to the magnitude of that, meaning same numbers, okay? Same numbers.